And now we will discuss some example which will be related to the vectors. So we start with the unit vector. So unit vector. So the unit vector, the magnitude of the unit vector is 1. So it's representing, or it's just telling us about the direction. So the unit vector, we talked about it in our previous lectures. So we have, for example, this is the x, this is the y, and this is the z-axis. So here the unit vector will be represented by the x roof. So here is the y roof, and here is the z roof. So the direction is the arrow is telling us about the direction. So the unit vector, since the magnitude is 1, so if we multiply it with any other vector or something, so nothing will change, but it is only telling us about the direction. So here in the previous lectures, I used the x roof, y roof, and z roof, since in the books the symbol for the x used is I roof, and for y is the j roof, and for the z is the k roof. So I will stick to the books since the books use the I, j, and k. So we will so it should not confuse you because I use these symbols, but I will use the x, y, x, j, and k in this lecture. Now the unit vector, we know that the vector is equal to the magnitude and also the direction. So the direction, for example, we have the vector which is represented graphically by a straight line. So here the line is telling us about the magnitude, and here is is telling us about the direction here. So what we are interested here in the unit vector. So the unit vector will be unit vector. So here is the vector divided by magnitude. So just the magnitude is here, so we have the unit vector. So example, so we will take the example. We have a vector which is 3i plus. So this is in the x direction I, and this is in the y direction. We want to know that the unit vector magnitude is 1, and we want to just prove it, and we want to just see if it's really 1 or not. So here the unit vector, we will use this relation here, so which is the vector itself divided by the magnitude. So the vector here, we will write the vector, which is this vector 3i plus 4j divided by the magnitude is the ax or ai. So I will just stick to ai plus aj squared under the root. So this is how we discussed this thing in our previous vectors lecture. This is just the example. So a is 3, ai is 3, and aj is 4 here. So we get 3i plus 4j equals so this is 3 squared plus 4 squared, so we get 3i plus 4j divided by 5. So the result that we get unit vector is 3 by 5i plus 4 by 5j. So this is the unit vector that we get. So this is the unit vector, but since we said that we want to know if the magnitude is 0 or magnitude is 1 or not, so we will just try to find its magnitude. So the magnitude of this vector, magnitude of a unit vector, so the magnitude we know, so this is the magnitude here, and we know that the magnitude is the x component square plus y component square under root here. So this is the magnitude. So we have the 3 by 5 square, so 3.3 by 5 is here, and then we have the plus 4 by 5 squared, which is the under the root. So we get 9, so this is 9 by 25 plus 16 by 25. So it is the 25 by 25, which is equal to 1. So we just proved that the magnitude of the unit vector is 1. So we first found out that the unit vector itself is here, and then we found that the magnitude here is 1. Magnitude of the unit vector. So now we talk about different vector operations. Vector operations. So we have the addition of the vectors, we have the subtraction. So these two are kind of the similar operations, and then we have the multiplications. So in our previous lectures, when we talked about the vectors, we talked about when we were talking about the lectures, I showed that how to subtract or how to add the vectors. For example, for the addition, we had the head to tail rule, and for the multiplication, we had the dot product and we had the vector product. But today we will talk about, or we will discuss some examples just to understand it better. You can see here that we are not, whenever we talk about the vectors, we do not mention or we do not discuss the division. The reason is that the vectors cannot be divided. For example, the north is a direction. We cannot say that the north divided by south or south divided by the west. So that's why the division of the vectors doesn't make sense. So we never talk about the division when it comes to the vectors. So we never talk about the division. So now we start with the addition of the vectors. Addition of the vectors. So in the previous lecture we talked about the two different ways of doing it. So one was the graphical method, and that was the head to tail rule. And the second one was the analytical method. Analytical method, and for this one we need a rectangular components. Rectangular components. So for the head tutorial, that's the graphical methods. When we are given two vectors, so with the graphical method, the head to tail rule, and we also have the other method that we discussed was the parallelogram method. So that we discussed there. So for the analytical method, when the rectangular components are given, for example, AX and AY and EZ, when they are given, then we use the analytical methods. And to find out the magnitude of a direction, we use the Pythagoras theorem, and we also talked about the trigonometric ratios. So for the Pythagoras theorem is a special case because we have when the angle of the triangle is 90 degrees, it's a right angle triangle, and the Pythagoras theorem is only valid when the angle is 90 degrees, mean for the right angle triangle. But today we will talk about the general case of the Pythagoras theorem, and the Pythagoras theorem is the special case of that triangle law. So the triangle law of the vector addition, triangle law of vector addition. For example, we have an angle. So previously for the Pythagoras theorem, we said that when this angle is 90 degrees, so, and this is theta, for example, so this side is the hypotenuse, this is the base, and this is the perpendicular. So we use the Pythagoras theorem, which was the hypotenuse square plus equals to perpendicular square plus base square. So this was the Pythagoras theorem. But here today we will talk about the case when this is, for example, one vector, and this is the second vector, and this is so this is A, this is B vector. So the angle here, you can see here, is larger than 90 degrees. So this is 90 degrees. So we will talk about a general case here. And then we will solve different problems with the different angles. And we will try to understand also the Pythagoras theorem here. So the general law for the triangle law is R equals A square plus B square plus 2AB cos of theta. So this is the general triangle law for the vector addition. What we see here, so this is, if we take only this part here, this is then the Pythagoras theorem. But we have this additional factor here. So if we look at it, so if we put 90 degrees here, means 90 degree cos of 90 is 0. So this part is 0, that if this is 90, the angle is 90, that it becomes the Pythagoras theorem. So it perfectly fits. Now we will use different angles, and we'll try to see what happens when we solve this equation if we use different angles. What will happen to the resultant of vector? So here today, this is the resultant vector. So we will try to see. So this is A here, this is A vector. So today this is the resultant vector, so we just use R. And we have the B, and this is the resultant vector. So we will use different angles. For example, we start with 0. So when the theta is 0 degrees, so if we use different 0 degrees, what will be the answer? And if we change the angle, what will happen to the answer, or the final resultant vector, or the magnitude of the, so this is the magnitude of the resultant vector. So if we, so R equals A square plus B square plus 2AB cos of 0 degrees. Since the cos of 0 is 1, so cos of 0 is 1, that means that the answer here is, so here I will write here, a square plus b square plus 2ab. So this is the formula for the a plus b whole square. So this is a plus b whole square and under the root this one. So they cancel each other. So the resultant vector, so what we get is a plus b. So this is the resultant here. So what we see here, when the angle is 0, means, so this is vector a and we have the vector b. So there is no angle between. So this is the vector a and this is the vector b. So when the angle is 0, we can see here that we can add these vectors like scalars. So it's a plus b here. So the angle is 0, so the vectors can be added like the scalars, like just a normal numbers. Now we take the example of 30 degrees. So the theta is 30 degrees. So first was the 0 degrees and now 30 degrees. So R equals a square plus b square plus 2ab cos of 30. And this is the under the root. So the answer is a plus b square, a square plus b square plus 2ab, and the cos of 30 is under the root 3 by 2. So these two cancels. So the resultant that we get is a square plus b square plus under the root 3 under the root ab. So what we get here, so under the root 3 is 1.7, which is smaller than 2. So what we see here, so the factor here, the factor here was 2, but right now it's 1.7. So when the degree, so that when the angle between the two vector was 0 degrees, the factor here was 2, but when we increase the angle, the factor here is 1.7, so it's the resultant is decreasing. So we will also try some other angles and try to see what actually happens when we change the angles. Right now, so we take the example 45 degrees. So R equals a square plus b square plus 2ab cos of 45 degrees. So under the root, and then it's equal to a square plus b square plus 2ab, and the cos of 45 is 1 over 2 under the root. And this is equal to a square plus b square plus 2ab under the root. And this 2 under the root is equal to 1.41. So what we see here, so we saw when the angle was 0, the factor was 2 here. So this is the factor is 2 here. So when we only concentrate the final answer, and here was under the root 3, and here this is equal to 1.7, so it's lower than 2. And here now it's further reduced, and it's 1.4. So the resultant is further decreasing when we increase the angle between the vectors. So now we try 60 degrees. So a square plus b square plus 2ab cos of 60. So the cos of 60 is 1 by 2. So 1 by 2, the 2 cancel. So I will write the final answer here. A square plus b square plus AB. So we can see here now it's even lower than 1.4. So here is 1, so here was 1.4, 1.7 and 2. So it's further going down. So now we try the 90 degrees. So R equals a square plus b square plus 2ab cos of 90. Since the cos of 90 is 0, as we discussed there, so the final answer we get is a square plus b square under the root here. So the resultant is a square plus b square. So this is the special case, and this is called the Pythagoras theorem. Pythagoras theorem. So this is the Pythagoras theorem, and this is the special case. So here it's, as we said, that it's only applicable for the right angle triangle. So now what we see here, so here was 1 and 1.7, we have here 1.4, and here the factor is 0. So it's, as we see, it's constantly coming down, it's going down. And now we use angle 120 degrees. So R equals a square plus b square plus 2ab cos of 120 degrees. So cos of 120 is minus 1 by 2. So minus 1 by 2, so we will have, so cos of 120 is 1 by 2, so we will have the resultant is a square plus b square minus ab. So now from 0, now it's minus 1 here. And the last one we try is 180 degrees. So the resultant here is a square plus b square plus 2ab cos of 180 degrees. And the cos of 180 degrees is minus 1. So it's a square plus b squared plus, sorry, this should well be minus 2ab, because the cos of 180 degrees is minus 1. So here we have the minus 2ab then. And here this a squared plus b squared minus 2ab is the formula. It's equal to 1 minus b whole square. So R is equal to a minus b whole square So they cancel, so A minus B. So what we see here, if the angle between these two vectors here, so this angle between these two is minus 100, so it's when it's 180 degrees when the angle, so we can just simply subtract like scalars. So when it was 0, so here, so this is A, and 180 degree will be like this, B. So when they are 180, the angle between these two is 180 degrees. We can subtract the vectors like scalars, just numbers. So what we see here, so in exams, this is very important for the exams. So what we see a pattern here. So when the angle was 0, the factor here was 2, and then when the angle is 30 degrees, the factor here is 1.7, and we further increase the angle, and the factor here is 1.4. Here, this one here, the final answer, and similarly it's going down from 1.4 to 1, and then 0, so then it was minus, and then it's, so what we see here, so the conclusion is that the resultant is inversely proportional to the theta. So we get something similar result. So the theta that we just discussed should not be confused with the theta that is generally used in the right angle triangle, which is in front of the perpendicular, or it's usually between the base and the hypotenuse. The theta that we discussed in our example is the angle between the two vectors A and B, which is shown here on your screen.